It's 4:30 now, and this is the last session of the day, so I'll crack on and go through things. So, for those who don't know me, hello, my name is Steve Capper. I work with the enterprise software teams within ARM, and this talk is about the kernel enablement of 52-bit virtual address spaces. And so I will begin the talk by introducing 52-bit virtual addresses, and then I'll go through the aspects of the kernel work so far. It's a sort of a status update. So the architectural support for 52-bit virtual addresses is an extension that has been added after the main ARM architecture was, thank you. So the main ARM architecture started with 48-bit virtual addresses as the maximum size, and 52-bit was added in ARM 8.2 as an optional extension. Now, 52-bit can only be utilized at the moment when one is running with a 64 kilobyte page size or granule. And Intel have similar extensions to their virtual address space where they have, I understand, was it 56-bit? And the way Intel achieved this is by adding another level of translation. Now, with ARM, we do not add a level of translation. If we want to go from 48-bit to 52-bit, our first level, our PGDs, just get a little bit bigger. So the salient point for 52-bit virtual addresses, which is for the kernel, is we do not change the number of levels of translation. We just make the first level a little bit bigger. So this means the kernel support looks a little bit different to the Intel extensions for 56-bit. So in Linux, I simplify things with virtual addresses. For Linux, I consider virtual addresses within the kernel, and I consider virtual addresses within applications. And both of these can be extended to 52-bit. So in the kernel, the principal reason one would want 52-bit virtual addresses is to be able to address a significant amount of physical memory. Now, one thing that is worth mentioning now is that in the kernel, one can already address 52 physical bits. So 52-bit physical address support is in the kernel. For virtual addresses, one would use this in the kernel if they had a large amount of memory in different places and the direct linear mapping was very big. So there's nothing in the kernel blocking physical addresses that are 52-bit. If we wish to introduce 52-bit virtual address support to the kernel, it is a little bit complicated because in the kernel we have baked-in assumptions about the number of virtual address bits being constant. So in the kernel we have a VA bits constant, and this determines how data is stored in the kernel to facilitate translation for whatever the VA bits is set. Now, kernel is quite hard to do. We also have to consider user space, and this actually might be more interesting for most of the audience. So with user space, again, we may wish to just deal with a large amount of memory in the application. User space virtual addresses are significantly easier to implement in the kernel because they do not require modifying a lot of the kernel structures. It's a lot simpler, the implementation. As a consequence of this, I have two patch series that deal with 52-bit. We have a patch series that deals with kernel virtual addresses, and we have an independent patch series which deals with user space 52-bit virtual address support. So I'll start with kernel. So I said before we have a few constants which are derived from a VA bits constant. With Linux in general, we wish to have a single kernel image that runs on multiple machines. So we can't statically compile 52-bit support for a kernel because it might run on an older system that doesn't have 52-bit support. and so it won't work. So the 52-bit support needs to be dynamic at boot time. When extending the kernel VA space size in the kernel, we have to go along and deconstify a few things. So a few things that are constant become variable, and we also have to change the way we arrange the memory. So I'm going to very briefly go through the deconstifying so the patches make sense, and I'm going to very briefly go through how we rearrange the memory for the kernel side. So deconstifying, at the moment in the kernel we just have a single VA bits constant. Now, if our virtual address size is determined at boot time, it can no longer just be one constant. So in the current patch series that I have, we have a maximum number of VA bits as a constant, we have the minimum number of VA bits as a constant, and we have the actual number of VA bits as a variable. And this actually significantly minimizes the disruption to the rest of the kernel. So data structures can use a constant, which is the maximum. When we're doing things like EFI memory mapping, we do the worst case scenario for distance using the minimum, and the actual we use where we actually need to know how many VA bits we have at runtime. I'm going to quickly go through the kernel memory map. So on Linux, the kernel memory map is undocumented because it's subject to change. I'm putting the kernel memory map up here to just show how the 52-bit support changes things in the kernel. So the important points that I'd like to convey in this slide, with the virtual address memory map in the kernel, half of the memory space in the kernel is dedicated to the direct linear map. And this is used by the kernel to address all the physical memory in the system. The rest, the other half of the virtual address map, is split up for everything else. So we have the direct linear map and everything else. Now, with this particular diagram, if we change from 48 bits to 52 bits, all these addresses here will move about. Now, in the kernel, it's not advisable to try and move the text segment and all the function addresses around when running with a different virtual address size. So if we can keep those constant, it'd actually make life a lot easier for the code and make the patches a lot less invasive. So what I decided to do was to swap. So the direct linear map now, in the 48-bit case, occupies the lower addresses, and everything else occupies the higher addresses. The advantage of doing this is when we switch to 52-bit, all these bits in grey at the bottom match up. So we can boot in 52-bit with very little change. And the KSAN region, we route that at the bottom, and it just expands upwards in this diagram. The important point here is the direct linear map is now significantly bigger, and this is what we want. This is the whole reason we want the 52-bit, is to have a bigger direct linear map. One negative aspect with this particular approach is that we have a gap here. Now, in this diagram, this gap doesn't look very big, but in real life, this gap is 5 times bigger than all that. So there's room for finessing this option, but the basic principle of flipping the address space around and growing it upwards in this diagram is the approach we're taking at the moment. So I'll talk now about 52-bit user space virtual addresses. Now, as I said before, to implement 52-bit user space addresses in the kernel, it's significantly easier because on ARM we have separate translation regimes for user space and kernel. So we can just tweak a register, make sure everything's big enough, and do things safely. So the user space patches for this are quite simple. The interesting thing that I'd like to go through, which probably is of use to everyone here, is how user space virtual addresses are advertised. So as I said before, when ARM version 8 was introduced, the assumption was that 48 bits was the maximum virtual address size. There is unfortunately software that makes use of that assumption. So when we extend the virtual address size to 52-bit, we have to maintain compatibility with the legacy software. So the way we maintain compatibility with the legacy software is to allow newer software to provide a hint to the kernel saying, please give me a 52-bit virtual address instead of just a 48-bit virtual address. And the idea is this hint is only employed by software that knows about it, and the rest of the software just is restricted back to 48 bits. So what we do is, with the kernel patches, with the mmap syscall, there is an address hint parameter. Most people just put 0 in there as a hint, but if one were to put a hint in there with the top bits here as non-zero, then the memory allocator will give a much bigger range back to the user space. And this is currently being reviewed. John suggested a tweak to this, but this particular scheme of hinting for a high address is employed currently by x86 and PowerPC, so it's quite likely the way we do things. So just to clarify as well, when we fire up a Linux process, we get things like shared objects, executable segments and everything. They get mmapped by the Linux loader automatically. With 52-bit support, they get mapped in the exact same place, so there's no perceivable difference. Similarly, the stack and VDSO and everything else, it all just looks like a 48-bit system. So we try our best to maintain compatibility with 52-bit. So just to summarize again what I said, if we are writing software and we are controlling the source of our pointers, so we perform memory allocation with mmap or malloc or whatever, then to maintain compatibility with 52-bit support, it should be okay. The time to worry about 52-bit support is if we are accepting pointers from somewhere else. So if we're writing a library and we are making assumptions about our virtual addresses being 48 bits, then we might have a bad time with the 52-bit support. Similarly, on x86 with 56-bit support and other architectures as well. So this particular point is of more interest to people who write JITs and people who write instrumentation tools that employ pointer tagging. If one employs pointer tagging, they should be careful with the 52-bit support, basically. But mostly everything else should function as normal. So the current status of the 52-bit support, we have, as I mentioned before, a patch set for the kernel space, 52 bits, and a patch set for user space, 52 bits. Now, if one is interested in testing their software for 52-bit compatibility, they just need to take the second patch set and run it in a suitable platform that has the support. So, and that is everything from my side. It's a very quick update for 52-bit. I'm happy to take any questions on the microphone. Thank you.
So I worked with more core implementation for libhuge TLB just for...
Oh, yeah.
No, I just fixed it, not that I created it. But my question is this going to break it? Because it implements its own more core for malloc. So do you see that you have to have a new wrapper for malloc, right? Calling mmap with the right flag, I mean, to have the new address space.
Yeah, so any extensions to more core, as long as they don't provide a high address in the mmap parameter, which I can't think of any reason why they would, unless someone's put -1 in or something, which they shouldn't do anyway.
Then they're all good.
Yeah.
And so the second question is about growing the heap without memory map, like dash break. if you grow the heap without mmap with sbreak,
Oh, yeah.
is that a problem?
So sbreak will just give this standard 48-bit behavior.
Okay, thank
So
you.
it's literally the only code path that changes is the mmap implementation. It looks for the address, and then, yeah.
So can we go back last slide?
Yep.
So when you talk about to test the user space 52 bits, so we just merge the total 5 patches or only the first one patch?
So to test in user space, we just need these 5 patches that were posted, I think, several weeks ago, and a system or a model that provides ARM 8.2 support.
Okay, so all the 5 patches are needed, right?
Just this.
Yeah, okay, okay, thank you.
Hey, asking for a friend. With mmap switching to 52-bit allocations based on size, what sizes
Oh, no,
were
no,
you
sorry.
thinking of?
Sorry, not size, hint address.
No, there's a hint address, but you also had the notes about John Masters.
Yeah,
switching
so
the size.
basically John Masters found a bug that we're going to fix, whereby what you could do is you could provide a low address and a really big size,
Yeah.
and then you get an allocation that goes to the full 52-bit, and that's wrong. So that's being changed to maintain full compatibility with the 48-bit case. So what will happen is, if one asks for something that's too big to fit in the 48-bit range, but they have an address hint within the 48-bit range, then mmap will tell them to go away with an error message, which is what it does currently. So that's just to maintain compatibility.
I'm sure my friend will rest easy. Thank you.
Yeah. Oh, hang on. Okay.
So a couple of bits in your diagram had 51-bit things. Could you
Yeah,
just
yeah,
explain
so-
when that, why and when?
Because it's half of 52. So this is 48 bits. This is half of the 48-bit range. This is 52 bits. This is half of the 52-bit range.
Okay. And the hint thing said 51:48.
Yeah, so the
As well.
hint address. So if you provide an mmap address which is too big to fit, if it's just like here or upwards, then it'll assume that you want a 52-bit.
Steve, can you go to the last slide, please? So that's not a question, a clarification, speaking on behalf of the ARM maintainers. So at the moment, we see no specific use case for merging the first patch set. So we are not going to merge this into mainline kernel unless we hear some concrete use cases for systems that needs to have 52-bit kernel virtual addressing support. What will progress instead is the second set of patches from Steve. So the ARM maintainers are very much keen in merging the second set of patches. So if you do have a use case for a system that make use of 52-bit virtual addressing support in the kernel, please reach out to me, to Steve, or on list if you have public information, so that we can make a case for progressing the first set of patches. Thank you.
Is that everything, guys? Okay. Thank you for your attention.